Dear colleagues, ladies and gentlemen, warm welcome to the IOER-Forum. My name is Jochen Schanzer. I'm going to moderate today's event. Please let me particularly welcome our speaker, Professor Manfred Laubichler from Arizona State University. Manfred, thank you very much for being here today. Manfred Laubichler is the Global Futures Professor and President's Professor of Theoretical Biology and History of Biology. He also holds the position as Director of the School of Complex Adaptive Systems and the Global Biosocial Complexity Initiative at Arizona State University. And he's now also the Director of the Decision Theater. Maybe you will talk about this later. He's a complex system science theoretical biologist and historian of science. His work focuses on evolutionary novelties from genomes to knowledge systems, the structure of evolutionary theory, and the evolution of knowledge. His undergraduate training was in sociology, philosophy, and mathematics at University of Vienna. And his graduate training was in biology at Yale University and in history of science at Princeton. He's an external professor at the well-known Santa Fe Institute and visiting scholar at the Max Planck Institute of the History of Science in Berlin, and external faculty member at the Complexity Science Hub in Vienna. He's also an elected fellow of the American Association for the Advancement of Science, a former fellow of the Wissenschaftskolleg zu Berlin, and vice chair of the Global Climate Forum, also in Berlin. Manfred, without further comments, I would like to hand over to you and look forward to your talk.
Yes, thanks, Jochen, and thanks for the invitation. It's great to be here. I haven't been to Dresden for a couple of years, so it's always interesting to see how fast things change. What I want to do today is talk about the origins of the Anthropocene. You're all aware that we live in the Anthropocene officially, eventually, as soon as our colleagues in geology get around to formally approving the proposal of the Anthropocene. But the timing or the stratigraphy of the geologists is not really what interests us. What we are interested in are the dynamics of the Anthropocene. How did we get there and where are we going? And during the pandemic, which I sort of spent in Santa Fe, my colleagues, particularly Jeffrey West and myself, found ourselves with some time at our hand. And so we did what proper complex system scientists do and what the Santa Fe Institute is famous for. We came up with a foundational equation, the Anthropocene equation, and I will sort of tell you all about how we got there, what it says, other than that it's a beautiful mathematical proof and therefore true, but it also connects very well with empirical phenomena. And we labeled the underlying dynamic the Anthropocene engine. So how do I move this thing? Thank you. So before we get into the mathematical and other details, I think I particularly like this image by Paul Klee and also Benjamin's quote, because it pretty much characterizes our situation today as much as it did Benjamin's situation in the 1930s. Namely that history happens anyway. Our problem is that rather than facing the future, we are looking to the past. And this is basically what this is. And science in particular has been very fond of looking to the past because that's where we have data, that's where we can test hypotheses. And we have done a much worse job in anticipating the future. And that's part of the problem why people don't take us seriously, because they want to ask us, what can we tell them about possible future? So I think it's, for us, really important that we face this dilemma head on and say more or dare to say more about the future, and particularly the future of the Anthropocene. So the challenge that we have is that we have entered the Anthropocene. And it didn't happen overnight, and it didn't happen in 1945 or whatever the official date will be. It happened as a consequence of very complex and long co-evolutionary dynamics between our species, other species, and the environment. As a consequence of those dynamics, we are currently shaping and engineering our planet at global scales. And therefore, but nobody will be surprised by that statement, we have sort of left what can be considered a safe operating space. There's a talk about planetary boundaries that we are pushing against. There are all kinds of crisis modes, collapse phenomena, you name it. Let's not get into the detail, but make this as a pretty safe statement. The world is insecure. And the challenges that emerge contribute to something that can be labeled as systemic risk and system failures. The systemic risk, I take no responsibility, ask Jochen, because we were at a task force of the Berlin-Brandenburg Academy and sort of thought about what systemic risks are from different perspectives. As I always like the intuitive definition, a systemic risk is a risk where you can take out an insurance policy for. And since the insurance industry is now rapidly retreating from insuring homes in Florida or in the west of the United States, or will happen in Europe too, you see that there are more and more systemic risks at large scales. Now, if you take this all together, what we are challenged with is that we need to come up with a new scientific understanding to meet those challenges. And as Jochen said, I come out of evolutionary theory. So if you look at major transformations throughout evolutionary history, there are those things, those events that happen on a daily basis, adaptation, speciation, everything that you can consider as relatively boring in evolution. But then there are certain events that are more interesting, and those are the so-called major transitions of evolution. Those major transitions are events in evolutionary history that led to a relatively dramatic transformation of systems. So here are a few: the origin of life, the origin of cellular life, multicellular life, and so on and so on. What they all have in common, that each of those major transitions in evolution lead to new types of organization in those systems. They lead to new types of the way energy is used and utilized in those systems. They reorganize knowledge and information flows through all those systems, as well as material flows. So a multicellular organism, for instance, is differently organized than a single cellular organism, and all of those counts. So one can find some general features of those major transitions in evolution by focusing on those system-level properties. Another consequence of a major transition is that you get emergent layers of complexity and different types of feedback regimes in those systems. And that will become important later on. And now, just as a preview where we are driving that the Anthropocene, in particular sort of its manifestation as the Technosphere, sort of all of the infrastructure and technology that we have created throughout human history, basically amounts to a major evolutionary transition. If you think about what those four main points are that characterize a major evolutionary transition: new organizations, new energy system, knowledge and information flows, and material flows. The Technosphere, basically, that's now another global sphere sitting on top of the biosphere, fulfills all those properties. So we have to look at the Anthropocene and the Technosphere through the lens of major evolutionary transitions. Now, that gives us a problem, because if you do this within the standard framework of evolutionary theory, which is sort of characterized here, we have no way of understanding what goes on. And that's why this sort of standard evolutionary framework is really not sufficient anymore to understand transformation. So this basically states what you all learned at some point, that there's a hereditary system, then organisms develop from into phenotypes, selection acts on the phenotypes, and whoever survives basically changes the frequency of genes in the next generation. That is not at all what evolution is really about, but it's still being taught to most students. So that says again something about the scientific system. What goes on is more like this. We labeled that an extended evolutionary framework. And what you see here are different types of feedback mechanisms that play a role. We realize that it's not only the regulatory networks that control those systems, particular development, that produce the phenotype in the first place. The phenotype, or all organisms or systems, creatively and interactively shape their environment. I mean, it's a process we call niche construction. So that's already a first feedback process. We call it externalization. Organisms or systems shape and transform their own environments, and thereby also have some level of control over the selective feedback that comes from the environment. So those are the two internalization feedback loops. So internalization one means basically the way we shape our environment changes the selection pressures that we experience. Feedback internalization number two, and more interesting one from a mechanistic point of view, is that whatever we construct into the environment also influences the basic operations of those biological or technological systems, so they directly interfere into development. Let me give you an example of how this can be thought about. So we have, over the last 250 years, synthesized several million chemical compounds that haven't been there before. And we have released them into the environment without thinking about it. There's a class of those compounds called endocrine disruptors. An endocrine disruptor is a chemical substance that mimics the actions of hormones. And there are quite a few out there. Now, if you think about how that affects development, a very complex process that now babies are born in environments that are full of chemical substances that haven't been there for all of evolutionary history. And it directly influences how those regulatory networks operate and the outcome of the phenotypes. Just one example, it's a somewhat speculative example, but I'm trying to get some colleagues to actually test this hypothesis. It is sort of an interesting observation that we now experience a much higher frequency of, let's be very neutral in the language, let's say confused gender identities, all the kinds of transgender issues. And in America, where I live, this is, of course, part of culture wars, and it's all woke and something else. But that's not really what goes on, because I know several people who have gone through this, and they're not doing that out of ideological, misguided beliefs. They're doing that because it's very seriously affecting their life. So what's going on? Why is there a higher frequency? And it's a higher frequency because we always had transgender individuals. But it's a higher frequency. And then you start looking at where there are clusters of transgender individuals. And often you can trace that they were born into environments that had high degrees of pollution. So an hypothesis would be that maybe the fact that we have a very delicate regulatory process of gender identity in the biological sense, that if you start messing with this through the chemicals we put into the environment, we change those outcomes. Still sort of a more speculative hypothesis. I could give you much more boring biological examples that illustrate the same thing. But it just shows that this internalization too that we have here is a very real phenomenon. So rather than having just phenotypes and selection acting on phenotypes, we have a picture of the evolutionary causality that takes into account all those additional and novel forms of interactions. So if we summarize this, the picture of evolution that emerges is that we have regulatory networks from genes all the ways or layers of the organismal complexity that are control the behavior, the development of phenotypes, and basically also the main explanatory feature of understanding evolutionary change. Those regulatory networks are also have to be combined with niche construction perspectives, because those highlight the multiple interactions between organisms or systems and their environment, as well as the existence of multiple inheritance systems. We can talk about that if you're interested in, but it's sort of a side story for what we want to say here. And then, for example, what we then get, if we combine those two perspectives, we get a fuller picture of the evolutionary process of the sort I just suggested before. Now, I said before that the Technosphere is a major transition in evolution. And this is an image from a paper that I'm currently writing with Jürgen Renn and Ricarda Winkelmann. And so the interactions between all the various Earth system spheres. And it's nice, we see everything interacts with everything else. We know that already. But what's really remarkable is how the Technosphere is different than all the other ones if you look at the temporal scales. Because all the other ones have nicely overlapping, and we can sort of model the effects of the hydrological cycles with the atmosphere and how that sort of affects the biosphere, and we have all those Earth systems models. But if you add in the Technosphere, and you add in that part of the Technosphere that operates on nanosecond base, and if you think that that's not important, the whole financial system operates on computational trade networks on nanosecond scales, and that pretty much influences everything that goes on, then we have an interesting modeling challenge, because we have not yet figured out how to integrate those temporal scales into systematic models of the Earth system at large. So that's the Technosphere. It emerged as an evolutionary transition. So now how did we get to that Technosphere? So let's start with an interesting observation. 10,000 years ago, we were basically behaving like the naked primate that we are in a certain sense, and we had a natural metabolic rate of around 90 watts. Currently, our social metabolic rate per individual is 11,000 watts, 2 orders of magnitude higher. If you do something what we like to do, particularly in the Technosphere Institute, you look at scaling laws. This is a scaling law for metabolic rates. And so 10,000 years ago, we were right there where we should be between the mouse and the elephant. And if you map ourselves now on this scaling curve, we are off the chart, because that's a log-log plot. So that's something that we need to explain. That's sort of, for me, that's the origin of the Anthropocene. How did we get from being right there where we're supposed to be to where we are now? That dynamic is the Anthropocene. How did we get there? Well, yeah, I'm not showing you all the fancy math we did, but that's sort of the easiest formulation of the Anthropocene equation. It's basically, if you take energy as a currency, then we have the basic social metabolic rate, sort of Y of n, and you can break it down into a maintenance rate and into a growth rate. And the N here is what we call an extended individual. It's no longer just our biological individual with the base metabolic rate of 90 watts. It's our social extended individual. It's us plus all of our infrastructure that we need to survive. Now, if you look at that and you take the accumulation over the last 10,000 years, you see an immediate problem. Because even if we would stop growing our population, let's say let's put the DE of n over dt 0, the majority of our energy consumption sits in the maintenance term of our built-up infrastructure, our technosphere. So even if growth would end, our energy problem wouldn't end, because in order to maintain the built-up technosphere, that requires almost all of the energy that we are currently using, because we don't really have that higher growth rate currently. And it's sort of flattening out anyway. So all of our current energy consumption, most of it at least, sits in our maintenance term of the technosphere. So this has some serious consequences. And it is sort of something that you can get with this equation. Now, this equation drives something that we call the Anthropocene Engine. And the Anthropocene Engine is an interesting phenomenon because in its most basic form, it's the closure of a positive feedback cycle between population growth, knowledge creation, and energy use. And it has some fascinating origins of roughly around 8,000 years ago, where there was what we call an early anthropogenic change that climate scientists sort of have established and now debating its significance, often labeled as the Ruddiman hypothesis. So from our co-evolutionary approach to a major transition, what went on there about 8,000 years ago is the following. At that time, our species was all over the planet. We have conquered every continent with the exception of Antarctica. Our ancestors, even though relatively small in numbers, engaged in a very large-scale transformation of landscapes, particularly through fire. Australia, North America, extinction of all the megafauna, part of the consequence of this. So there are many sort of interesting stories about that time. So from my point of view, this extended evolutionary framework, this was a very early act of global niche construction. And what the most interesting measure of that global niche construction is a slight increase from the simply physical models. We should at that time entered another cooling period, but we didn't. And it was that early anthropogenic niche construction that put enough CO2, completely unintentional because nobody did it in a coordinated way, but the cumulative effect was that it stabilized the climate of the Holocene. Now, stabilization of that climate enabled some initial population growth, which allowed those ancestors to extract enough knowledge about their environment to start agriculture and domestication, which provided more energy, which provided more population, which provided more knowledge, and you see where this is going. So basically now we have that Anthropocene engine running. And it's from a systems dynamics point of view, it's a closed positive feedback cycle. And so this is sort of the underlying mechanism that drives this growth equation that we call the Anthropocene equation. So what that has in common, and if you sort of look through Earth's history, since this is a growth equation and it has an exponent that is larger than 1, so it actually will always approach singularity points or collapse points. And this is a very schematic representation of the history of the last 10,000 years or so, because we can calculate that we have approached collapse points before, but we always got ourselves out of a pickle in a way by some technological innovations. And the problem was that each of those innovations that we introduced in the system to avoid a collapse point under the previous systems dynamics accelerated the engine. So we are now in a cycle of growth, approaching collapse, avoiding collapse, so technological innovation, which speeds up the approach of the next collapse point. And so this is what where Stefan and others sort of and historians labeled the great acceleration dynamics. But the great acceleration is only the last out of several ones that we have already experienced over the last, let's say, 8 to 10,000 years. So we did this, and so we have the equation, and we parameterized this with the whole data set of where Stefan and others, and added a few more. All those hockey stick curves that you're familiar with of the great acceleration. And then, of course, the first thing you do if you have a well-defined mathematical equation, you want to know when is the next collapse point. So when is the next singularity? So we calculated it. And then there is a simple mathematical test, because if it's right and the data are accurate, then the approach towards the singularity plotted on a log-log scale would be a straight line. So this is a formal test. So we did this, looked pretty good, looked pretty depressing, because the initial singularity point that we had was in around 2036. But then we looked a little closer and said, well, there is a little bulge in there. So there might be a breaking point in there. So we analyzed the dynamics, and we found a breaking point where the dynamic changed. So then you have basically one from the 1940s to about the mid-1970s, and then another slightly different dynamic from the mid-1970s to now. And so this breakpoint analysis pointed out that somewhere in the mid-1970s, the dynamic changed. And this is sort of a strictly mathematical, data-driven approach. No thinking about what actually went on in the 1970s. And then we started talking about this. And everywhere I go, and where Jeffrey West goes, people get all excited about this. Is really interesting because we tell you what happened in the mid-1970s. Oil price shock, end of the gold standard, beginning of the real IT revolution in terms of personalized computers. So, an endless list of social, technological, cultural events that sort of happened in sort of a period in the mid-1970s that make it very plausible that the change in the dynamics that we picked up through our formal analysis is actually real and can be traced to some ongoing historical events at that time. So we analyzed this, and most times you have a breaking point around 1970s. So if you don't believe me, here's some data. Doesn't really matter. Some of them are later, but the majority of them are in the mid-1970s. Okay, so this is sort of a straightforward global picture, because those data of the great acceleration that we analyzed were global data. Of course, we know that the dynamics is not uniform across the globe. So this is something from work that Jonathan Donges did. They also looked at the great acceleration data. And insofar as they could find some more regionally specific data, and then the data challenge becomes huge pretty fast, because it's very difficult to get very high resolution data for specific regions. You have to sort of try to get them with some approximation, but all those caveats, it's clear if the darker colors is an earlier acceleration dynamics and the lighter colors is later, it basically shows how you can identify that the overall global dynamics is actually composed of different local dynamics that operate on different temporal scales. So we want to go much more in depth into this sort of more regional understanding, and then also trying to figure out from a systems perspective, what are the interconnections between the dynamics at different regions and the different temporal regimes in that dynamic. So this is the beginning of a rather extensive research project here. Then I show you something else. This is work that I've been doing with Jürgen Renz's group, in particular with Jochen Püttner. And so there we focused on CO2 emissions and population growth dynamics. So if you plot those two together here, population blue, CO2 emissions red, you see a sort of a predictable way that they grow in a very much the same pattern. More people emit more CO2, but that's still sort of very, very coarse-grained. So if you look into this a little more in depth, then, and do a scaling analysis, and then you see that there are actually different regimes and different breakpoints in the relationship between population growth and CO2. So this is from roughly, I think, 1800 to now. And you see there was a regime in the early 19th century that was superlinear scaling. So that means we really per capita increased our CO2 output. That accelerated in the second half of the 19th century to 1871. Then it sort of became a little less steep. And then you have a real break around 1914, where there are lots of interesting things connected to World War I, similar then later on to World War II. But don't care about that. Think about the dynamics, how all of a sudden the scaling curve flattens. And so what could be explanations for this? Again, you have to then go into the more historical record. And what you see here is if you correlate that with the actual use of fuels that contribute to CO2 emission, then you see that the 19th century is basically the age of coal. And the flattening of the curve in 1914 means that coal basically flatlined, and all the increase in burning happened basically on oil and later on gas. So after the oil price shock in 1974, oil flatlines and all the increase basically is gas. So, of course, those different fuels have different amounts of CO2 emissions. So then you can see that what you pick up from the scaling analysis can be causally explained, at least partially, because there are other factors that play a role, by shifts in the energy regimes that drive our technosphere. So those are some of the more detailed studies that we are now currently pursuing in the context of the scaling analysis and the Anthropocene equation. This is sort of an interesting thing, because if you would have projected into the future the growth regime from the 19th century all the way to the 8 billion people that we have now, we would have had a 680-fold higher emissions than we currently have. And then you can do the same thing for what actually the effect of gas versus oil is. If you project sort of from 1970 forward and just with oil, we would have about a 3-fold higher emissions compared to the actual emission, because we changed our fossil fuel mix. So those are the kind of things that you can amuse yourself with if you have those kind of data. But I think it tells interesting stories, because it tells stories, in particular, what we had before about approaching a collapse point. If you would have stuck with coal, our technosphere and our sort of combined system would have collapsed by now. So the shift from coal to oil and then gas were technological innovations that basically avoided a previous collapse. But of course, as you see, we grow up pretty fast, and now we are very high, and we have a big CO2 emissions problem right now. And so we are approaching several collapse points, and we have to see how we can get out of those. Okay, so what can we learn from that? Well, based on going back to evolutionary models, all complex systems, complex evolving systems, are governed by regulatory structures. They construct their own niches. These dynamics introduce interesting feedback mechanisms into those systems. And what we know, and this is a more general result from complex system science, so you're all familiar with this, that if you have a dynamically stable system, it depends on having the right kind of balance between positive and negative feedback loops in the system. It needs to be able to grow, that's the positive part of it, and it needs to basically be controlled, and those are the negative feedback loops in the system. Now, what we have done over the course of human history, in particular over the last 10,000 years, and this is sort of the ones described by this Anthropocene equation, we have eliminated negative feedback out of the system over the course of human history. And you can say agriculture, which gives you more of a control over your food supply than hunter-gatherer, once it sort of is fully functional, is the first one where we eliminated negative feedback. Medicine, you name it, but there are many ways how we have eliminated traditional sources of negative feedback from the system. And we closed the positive feedback loop between population, knowledge, and energy. So that's sort of the Anthropocene engine. And the consequence is what we are all familiar with, sort of the continuous acceleration of human history and the, at least temporary, emancipation of humans from their environment. And that basically led us to where we are with the current crisis. So what can be done? So from sitting here as the director of the School of Complex Adaptive System, I can sort of preach and say, well, we have to introduce negative feedback into the system. We are doing it, we are starting to shoot at each other again, but that's maybe not the kind of feedback that we have in mind here. So what we have in mind are more of the sort of values, norms, laws, and regulation that make up the social regulatory system that we can also observe in the course of human history. And so currently finishing a paper which I fully expect will get me in a lot of trouble. So in a major transformation of evolutionary theory, and that's what I spent many decades doing, was the recognition that we need to understand those gene regulatory systems that control the expression of other patterns of genes, and are actually also give us with a mechanistic understanding of evolutionary change. Because, okay, biological, the organismal system are controlled by gene regulatory networks, that societies are controlled by social regulatory networks. So I'm defining those social regulatory networks in brute force analogy to the gene regulatory network. So that's why I will get beaten up when I'm used to it. But the reason why we're trying to do this in this very somewhat reductive way is because in biology we have learned that by tinkering with those regulatory systems, we can actually shape evolutionary outcomes. So if the challenge right now is to transform global societies in such a way that we don't collapse, then the only way that we can do this, and we don't want to just kill each other off, which is sort of what we're doing right now, would be to change those social regulatory networks in such a way that we initiate a different type of dynamics. I mean, again, that's easy to say ex cathedra from a complex systems point of view, and the political reality and social reality is more complex, but at least it gives us a way to think about what needs to be done. And so we need to learn, there we can again learn from the structure of those gene regulatory networks, because they have very specific identifiable complex systems property or network properties that can be tightly connected to particular outcomes. So I'm not saying that we have to do exactly the same, but we have to do functionally the same in defining what this social regulatory network should be. And so there are two types of regulation. There's sort of traditional hierarchy, or there's lateral regulation. And again, we need the right kind of balance of both. And that brings us to sort of interesting questions about the role or the problem of nation states versus global civil society. So one of the lessons of why we haven't dealt with climate change in any effective ways because we left it to nation states and their sort of hierarchical organizations, which then create, on the one hand, a circus called COP, and on the other hand, sort of things like the Paris Agreement that is celebrated and then ignored. So, it's all a consequence of non-accountability on the level of nation states and interactions with nation states. So in what way can global civil society, whatever shape that takes, be a different form of regulatory control? But also the role of scientific knowledge. And I think we are a big part of the problem, we meaning scientists, and over the last several centuries. And in order to redeem ourselves, so to speak, we should also become part of the solution. But that means we have to change some of our ways. And in the sense that we can no longer just produce pure knowledge and say, well, what's could be done with the knowledge is not our problem. I mean, this is sort of somebody else's problem. I think we no longer have that luxury. So the science-society interface needs to change rather dramatically. And that brings us to things that you're doing here at the Institute anyway, sort of more broad, integrative, and transdisciplinary approaches to knowledge generation. So the way we do this or try to do this at ASU, and Jochen mentioned it, we have a facility called the Decision Theater, which I inherited, and have now sort of started a transformation process. Because the Decision Theater in its previous incarnation was what I call a technocratic fantasy. So you build a complex systems model, you have certain points where you can intervene in the model. You bring decision makers in there, you impress the hell out of them because you have 7 screens and a sort of impressive facility. And you say, look, you're a decision maker, you can change this. And if you make this decision, we can tell you what the outcome will be. If you do something else, we can tell you what the outcome will be. And therefore, we shame them into doing the right thing. Of course, it's never worked that way. So what we are now trying to do with the new version of the Decision Theater is to use it much more as a discovery tool for transdisciplinary knowledge generation, where the science is at the table and the data are at the table and the models are at the table, but also the knowledge of participants and not just sort of deciders or decision makers, but everybody who is affected by the problems. So we are doing this also here. This is pictures from a Decision Theater event that we had in the Haus der Kultur in der Welt in Berlin just before the pandemic. And so there were people that we sort of recruited, but there were also really decision makers. The guy sort of in the lower picture next to my beard is a CDU-Bundestagsabgeordneter, for instance. So we had a broad level of participation, and the way this works, and it works actually very well. So you demonstrate and introduce a model. This is a model about the mobility transition in Germany. And you then form small groups, and those groups have to then discuss what they're willing to do, and what they're willing to do in 2 categories: what they're willing to do individually or as households and families, and what they would like to see in terms of policy changes. And then they make those things on the iPad, so they have sort of values that they can sort of change in there. And then we can project on the screens, if we would realize what you decided, this would be the outcome. And the ultimate outcome there is, do we actually get closer to the reduction targets of CO2 emission in the mobility sector? So this is something that works actually pretty well, and that we are now further developing in the context of this Decision Theaters. So the Decision Theater, the way we conceptualize it now, less a technocratic fantasy, but having basically 3 roles. One being science communication, so that we not just treat people said, well, science is a black box. You don't understand it anyway. We tell you what the output is. So we open up the box, we explain the models, we let the individuals or the public participate also in the creation of those models. We don't shy away from the difficulties of the problem. Rather, we emphasize and create awareness of the difficulties of the problem. One element that we found that works extremely well in the context of multi-agent models is that if you set them up in an interesting way and not too schematic, you really bring in the participants into the process because they can identify themselves as agents in the model. So one of the techniques that we are deploying is that we are building our multi-agent based models based on what's called an artificial representative population of a region. So you explain what that is, and then everybody sort of finds themselves somewhere in the model, and that sort of breaks down that wall between science and the public. And of course, you have to, not me, but we have people who can do that very well. You have to, if in those events, those decision theater events, they are facilitated, and the quality of the facilitator and how they can produce narratives that bring people into the process is the most essential part of a successful decision theater event. So that's an important part of it. And of course, the interesting thing is then once you demonstrate the model and you form those groups and they have their iPads where they can control the model, then that allows the participants to experiment with the model. So what we are building those decision theaters ultimately for is that they can become decision support systems. So in that sense that we bring in data and empirical facts and models that generate possible scenarios for the futures, that everybody who sort of goes through those events shares a knowledge base, so there's a common base. And of course, what's very interesting to observe in those group discussions is how then, when there is something that everybody sort of was introduced to and that sort of represents the problem, how people become aware of their own assumptions and backgrounds. And we have never had, anyway, some problematic discussions, although we had some interesting ones. I can tell you stories. But even there is a consensus of civility and exploring assumptions. And of course, we make those assumptions explicit. And so what this amounts to is sort of a co-creation of knowledge. Because also one of the sort of successes of a decision theater approach that we are now pursuing in the third generation has to do that you upfront say, look, what we present you here is sort of a model zero, because this is how we scientists sort of represent the problem. But we are also here to learn from the participants, because the problem in the real world often looks different than the model or the problem in the laboratory. And so we learned certain things. So, for instance, we did in Berlin a decision theater. That was the one that I showed you the pictures. And so there was a category, public transport. And all that we sort of had so far on what they could select and change parameters with has to do with the kind of technocratic idea where, how the frequency of public transport, how far out, and what's the average space between stops, all the kind of technocratic things. And then, the first thing we learned, and even though it wasn't strictly built by males, but the first thing we learned at that event was that the women in the room said safety, lightning, because that may influences the decision to take public transport. And we haven't thought about that, when we built the first generation of the model. Now it's in the model. So you have those iterative interactions with people so that you can even learn what the dimensionality of the problem is as it presents itself to the people affected by it, because that is different from the way we think about the dimensionality of the problem. And that is once you communicate that, then that becomes a very engaging part of those decision theater activities. And you, of course, say, well, there is not one model or even one goal, but it is a way of talking about problems in a more systematic way. And so that those models are always sort of work in progress. So this is how we are trying to translate from the kind of abstract science that we have to the real solutions in the world that we are trying to transform in a way that our kids and grandkids still have a world to live in. Okay, I'll leave it at that, and thanks. Here are some of the collaborators of this work.
Thank you very much, Manfred, for this talk, which provided us an overarching perspective on the Anthropocene, unfolding the driving forces and the mechanisms underlying this Anthropocene, and doing this on the basis on evolutionary theory, but also reflecting on the differences between the natural process and the societal processes, and at the end, even opening a perspective on what could be done in the future, what could be the role of science. And I fully agree with you that maybe the current way science operates need to be amended by this understanding you proposed as a responsible science and being more comprehensive and being more interactive with society. Thank you so much. I think this was really an impressive contribution also to the discussion in the IOR, but I'm certain also beyond. I also thank all participants to this meeting. Thank you very much.